In this video, we're going to cover carbonyl condensation reactions. In particular, we're going to cover the aldol reactions and their various variations. The aldol reactions are the addition mechanism for carbonyls. We're also going to cover the Claisen and related reactions. These are all substitutions. The Michael reaction, the Robinson annulation, and we're going to go over retrosynthetic analysis of these condensation reactions, which means we're going to be looking at how to determine what starting materials were used to make the final condensation product. Now, in general, what do we need to know about carbonyl condensation reactions? Essentially what they do is they condense two carbonyls into a single molecule. And to do this, an enolate nucleophile must be created by deprotonating the alpha carbon of one carbonyl. Then that enolate will react via either a substitution or an addition reaction by attacking the electrophilic carbonyl carbon of a second carbonyl. Now in the Michael reaction, addition occurs by attacking the electrophilic beta carbon of an alpha-beta unsaturated carbonyl. We'll get to that when we review the Michael reaction. The aldol reaction. The aldol reaction occurs when an enolate of an aldehyde or ketone reacts with another aldehyde or ketone via the addition mechanism at the electrophilic carbonyl carbon. As you'll see, one potential product of this reaction is called a beta-hydroxycarbonyl. Sometimes the reaction continues past this point, and the hydroxyl group can be eliminated via a mechanism called E1CB, and that will form a different product, an alpha-beta unsaturated carbonyl. We'll cover the E1CB mechanism after this one. So first, let's take a look at what we have. We have an aldehyde here, and we know that we're dealing with enolates. So I'm going to draw in one of the alpha hydrogens, because we know we should be removing it to create an enolate in this reaction. So when we react with the lone pair on the OH group, what we're going to do is we are going to remove this, and we're going to create an enolate at that alpha carbon position. Enolates are nucleophilic. So what's going to happen next is we're going to take this enolate and we are going to react it with the original aldehyde. And we know that aldehydes have an electrophilic carbonyl carbon, and they can undergo addition mechanisms. So since we have a nucleophilic enolate, what's going to happen is the nucleophilic position, this lone pair, is going to attack the electrophilic carbonyl carbon and send this bond up. This reaction should look very similar to any addition reaction at a carbonyl because that's exactly what it is. It is simply just an addition. So once we do that, when we draw this, we should be very careful in what we're doing. So let's draw what remains of the enolate. First, we'll draw that in red. We'll keep this color-coded. And now, what we did is we connected the alpha carbon to the carbonyl carbon. So I'm going to draw that new bond in green. So there's our new bond right there. And then where are we located? We are located at what was the carbonyl carbon, but now we turned that carbonyl carbon into just a carbon that's bonded singly to an O negative. We still have the hydrogen, but we don't need to draw it, but we also have the methyl group coming to the right. And that's what we end up getting there. Hopefully the color coding helps you out. The last step, of course, is that we're simply going to protonate this. So the last step, we're just going to take our water and the lone pairs on that O negative are going to deprotonate the water, giving us our final product. Now, as is the case for all reactions, we should, at the very end, check to make sure that we don't need to worry about stereochemistry, carbocation rearrangements, or resonance. So, do we have to worry about any of those things here? Well, this is an addition reaction, and we're going from something that was trigonal planar, which is the carbonyl carbon, to something that is now tetrahedral, which means that we had a 50-50 chance to attack from the top side of the trigonal planar molecule, or the bottom side of the trigonal planar molecule. So because of that, we should have to worry about stereochemistry, so we can simply pick something to put on a wedge and pick something to put on a dash, and then make sure we draw the enantiomer of it. So after stereochemistry is considered, you can see the products here. Now, of course, I did mention there's something else that can happen at the end here, and that is the E1CB mechanism, which I'll show you now. Now, about the E1CB mechanism for aldol reactions, it stands for Elimination Unimolecular Conjugate Base. And what it is a special elimination that occurs under basic conditions, and it may or may not occur at the end of an aldol reaction, but if it does, it yields an alpha-beta unsaturated carbonyl rather than the beta-hydroxycarbonyl that we got as a result of the last problem I showed you. Now, the E1CB mechanism always occurs at the end of an aldol reaction when the hydroxyl leaving group is adjacent to a carbon-carbon double bond or a benzene ring. The resulting product is favored due to that extra conjugation we'll get. Likewise, the E1CB tends to occur after intramolecular aldol reactions, which I'll show you later in this video. In the situations where the E1CB mechanism always occurs, the beta-hydroxycarbonyl cannot be isolated. So let's see what happens here. We're taking the product from the previous reaction, and we're going to continue the reaction into the E1CB. And what happens is we're going to remove this acidic alpha hydrogen with the base. That's going to create an enolate. Once that enolate is formed, it is then going to kick off the OH and form a double bond between the alpha and beta carbons. That will leave us with an alpha-beta unsaturated carbonyl right here. So for some extra practice, let's go through another entire aldol reaction. So on the left here, I have a ketone, and I'm noticing that we have one alpha hydrogen, or one unique alpha hydrogen here. And what we're going to do is we're going to deprotonate the alpha carbon and make our enolate. The enolate, being nucleophilic, is then going to react with another molecule of that carbonyl. And I'm going to draw it the opposite direction because it'll be a lot easier to carry out the reaction when it's facing this way, for drawing purposes anyway. So we're going to let the enolate, the nucleophilic enolate, attack the electrophilic carbonyl carbon. So from negative to positive, and that's going to send this double bond up to a single bond and give the oxygen the lone pairs. And then when we draw this, again, we want to be very careful about what we're connecting. So again, I'm going to switch. Our new bond is going to be in green, and this connects our alpha carbon to the electrophilic carbonyl carbon. So now we have to say what is located on that electrophilic carbonyl carbon. There's still a methyl group, so we're going to draw that methyl group in, and the double bond O turned into a single bond O negative, and we still have the benzene ring attached. Of course, after that, we have the easy step where we simply protonate with H2O. What you should notice at this point, however, is that the hydroxyl group is adjacent to a benzene ring, which means we are always going to do the E1CB mechanism. What's nice is we don't need to worry about stereochemistry when we do this because we're going to be making a double bond. So we do need to remember, however, that we are going to do the E1CB. So we're simply going to take that OH minus and remove this other alpha hydrogen. And of course, once that enolate is created, it is going to form a double bond and kick off the OH group, giving us an alpha-beta unsaturated carbonyl. And hopefully here you can see that we just formed a very conjugated final product that is conjugated not only with the other carbonyl, but with the benzene ring on the right. That's the driving force for the E1CB always happening, the extra stability as a result of that conjugation. Crossed aldols occur when you have two different aldehyde ketones and mix them together with a base and water. Multiple products will be made if both carbonyls have approximately equally acidic alpha hydrogens. In these cases, the reaction is not synthetically useful because too many products will be made. Crossed aldols are synthetically useful when only one carbonyl has an acidic alpha hydrogen, or when one carbonyl has an alpha hydrogen that is significantly more acidic than the other carbonyl. Let's take a look at this example where I have a red carbonyl and a blue carbonyl that are different from each other, and we throw them together with our base and our water. You can see that I have an alpha carbon here that has alpha hydrogens, and I also have an alpha carbon on this blue molecule that has alpha hydrogens, and these are not going to form the same enolate. So that means we're going to get a total of 4 different aldol reactions that are possible. You can see these on the left. So with the first one, we're going to take the red molecule, we're going to create its enolate, and then we're going to react it with another red molecule. In the second one, we're going to take the red enolate, and we're going to react it with the blue carbonyl. And then the last two, it's going to be the blue enolate for both, reacting with one of each. So you can see we're going to get 4 different products here. And again, that's not going to be synthetically useful. You can see here that I have all of the intermediates drawn out, and then all of the products as well. I do want to point out 2 things about those products. First, yes, if we wanted to, we could continue this reaction and have it undergo the E1CB mechanism. However, this isn't a requirement because we don't meet the times where we actually have to do it every time. And then second, we do want to consider stereochemistry. So again, we're going from trigonal planar to tetrahedral in all of these examples. So we should have it represented with having a wedge or a dash and both enantiomers. So I'm going to use the shortcut that's not technically allowed to use, so don't do this on a test or anything. But we're going to use the squiggly line representing that we're going to form both enantiomers for all of these products. A directed aldol is similar to a crossed aldol, but the enolate is selectively prepared first, usually with a strong non-nucleophilic base, such as LDA, under kinetic conditions. And this happens before a second carbonyl is added. So this reaction that I have right here is pretty straightforward. The first thing we're going to do is we are going to deprotonate the alpha carbon on this ketone. We're going to use LDA under these kinetic conditions. I'm not going to draw out LDA because it's a large complicated molecule, but we are going to form the enolate at the least substituted side and get the kinetic enolate. And once we have the kinetic enolate, now we can react with the second carbonyl. So once again, we're simply doing an addition. So we are drawing our arrow from our nucleophilic enolate to our electrophilic carbonyl carbon and carrying out the addition reaction. And of course, at the end, we should have a third step here where we treat this with water. At the end, we are going to have a stereogenic center, or we can carry out the E1CB. If we carry out the E1CB, we'll get the alpha beta unsaturated carbonyl, or we can stop here and isolate this. But again, if we do want to care about stereochemistry, so we'll get the wedge version and the dash version, or I'll just draw this squiggly line for us. For intramolecular aldol reactions, an enolate formed on a dicarbonyl will react intramolecularly if a 5 or 6 membered ring can be formed. The E1CB mechanism occurs at the end of intramolecular aldol reactions, yielding alpha-beta unsaturated carbonyls. So I have some steps listed here to help you with intramolecular aldol reactions. So if we look at the reaction down on the bottom here, the first thing we're going to do is we're going to locate all the alpha carbons that have alpha hydrogens. So this is a dicarbonyl, so we're looking at here, here, and here are all alpha carbons, and they all have alpha hydrogens. Notice the one on the right, that's a tert butyl group, so there are no alpha hydrogens there. So now we're going to focus on each one of these. And what we're going to do, with step 2 here, count the number of carbons from the alpha carbon to the opposite carbonyl carbon. So let's start with this one right here. So this is an inclusive counting, so we're going to count this alpha carbon. 1, 2, 3. Notice that's too small. We want to have 5 or 6. So we know we're not going to do anything with that alpha carbon. Same with this one right here. We're going from here to the opposite carbonyl. Again, that would only form a 3-membered ring, so that one's also not acceptable for an intramolecular reaction. Finally, we look at the one on the outside, and in this case, we have 1, 2, 3, 4, 5. So this one's going to work. Sometimes it will only work when we have the alpha carbons on the inside if it's a longer molecule. Other times it'll only work when we have a shorter molecule and we use the outside alpha carbons. Either way, you should check on them to make sure you have the correct number before you attempt to do an intramolecular aldol reaction. So we know we're going to remove that hydrogen. So let's draw that hydrogen in. And the same thing that's going to happen in all aldol reactions will happen here. The oxygen is going to remove the hydrogen, and we're going to create an enolate. As you would expect now, that enolate, being a nucleophile, is going to do an addition reaction by attacking the electrophilic carbonyl carbon. This is where a lot of times students get confused on how to draw the next step. So what I like to do is I like to redraw in my numbers, so 1 through 5 here, and I know that I'm connecting the 1 and the 5. In other words, I'm making a 5-membered ring. So I'm going to draw a 5-membered ring. And I'm going to number this ring from where I started, so 1, 2, 3, 4, 5. And I know that the 1 position was my original alpha carbon, and I know that that 5 position is where the double bond O turned into a single bond O, and of course we know that we protonate it. So I'm actually going to skip the step where I protonate it because I don't want to draw this twice, because the point is we can get to the answer quickly. So I know that at the 5 I am going to attach that OH there. And then after I do that step where I attach the OH, which we will remove shortly in the E1CB, we're going to draw everything else at the appropriate numbered carbons. So if we look at the previous molecule before we had the ring, you'll notice at the 2 carbon, I should still have a carbonyl. So I'm going to put my double bond O there. And what do we also have at the 5 carbon? I also have this tert butyl group coming off the 5 carbon, so I better keep that on there. So at the 5, I have this. So again, really it's just making sure that you draw the appropriate sized ring and then go back to the other molecule and see what we have there. So then, of course, the last step is we're going to remove the OH in the E1CB mechanism. Here's where I'm going to stop drawing steps in the mechanism. Technically, I already did since I skipped the water step. And I'm just going to write, we're going to carry out the E1CB here. E1CB. And that is going to allow us to put a double bond between the alpha and beta carbons when we remove that OH. And those are some steps to do the intramolecular aldol reactions a little bit more quickly. Claisen reactions occur when an enolate of an ester reacts with another ester via the substitution mechanism. Remember, aldols are additions. And this, of course, occurs with the electrophilic carbonyl carbon. Now, after the substitution is complete, the base that was used to create the enolate removes a second alpha hydrogen, driving equilibrium forward towards the products. An acid must be used in a separate step to form the final neutral product. Only esters with at least 2 alpha hydrogens can undergo Claisen reactions, and again, that's because we are going to have to remove a second hydrogen from the original ester in order to drive the equilibrium forward. The product that we get is called a beta keto ester. Now, I'm not going to show a crossed Claisen reaction because they are so similar to crossed aldol reactions, and that they're only synthetically useful when one of the esters has an alpha hydrogen available. In this top line here, I have two different possible reactions. Now notice in the first one that at the alpha carbon position I have two alpha hydrogens. That means when we do this, we will get a Claisen product. However, in the second reaction, notice that there's only one alpha hydrogen, and the requirement is that we have two. So here we're going to get no reaction. So let's explore why we'd get no reaction by actually looking at the entire mechanism for that first reaction there. So first, let's draw in one of the alpha hydrogens here, and we know we're going to remove it with that base, that OET negative. That's going to give us the enolate. And once we have this enolate, what we're going to do is we're going to react the enolate with another one of these esters. And as I mentioned before, this is a substitution mechanism, and we can tell because we have a good leaving group. So that OET is a good leaving group. So we're going to do a substitution mechanism, not an addition mechanism. So the nucleophilic enolate is going to attack the electrophilic carbonyl carbon. And I'm not going to show both of these steps in two separate steps. I should, but for the purposes of not having enough space on the page, and because I don't want to have to redraw this a bunch of times, I'm going to send this bond up. Technically, we should draw this. And then it's going to come back down, and it is going to kick off the leaving group. Again, that's just the substitution mechanism for a carbonyl. So once we do that, that is going to give us a product that looks like this. And again, I'm going to be very careful with how I draw this, because we're connecting the alpha carbon from the enolate to the carbonyl carbon of the other ester. So what I'm going to do, notice I have this additional methyl group here, and I'm going to draw that going downwards. That way it's not in the way. I want it to be really clear that the new bond is going up to the right like this, just because it's easier to visualize when we draw it this way rather than draw that carbonyl on the bottom side. I'm just going to draw that methyl group on the bottom side instead. So that's our new bond right there. And where are we located now? We're located at the carbonyl carbon. And notice it's a substitution, so we kicked off the OET group and regenerated the double bond O. So we still have a double bond O here, and now we have this ethyl group as well. So, although this is actually the final product, it's not the end of the mechanism, because this mechanism is driven forward by the removal of the other alpha hydrogen. If we can't remove another alpha hydrogen, then equilibrium is actually going to favor the starting material and not the final product. So what's going to happen now is we have to do this if we're drawing the mechanism. If we're not drawing the mechanism, you can just stop there and that's going to be the final answer. But if you're asked to draw the entire mechanism, we have to continue this reaction. So we have our base, and we have this particularly acidic alpha hydrogen now, because now it is between two carbonyls, so it's even more acidic than was the original one. So now we're going to remove this, and that's going to put an enolate in this position right here. Once we have that enolate, that's when we can go to the second step, and that is when we add in H3O plus and simply remove the enolate. So we have our H3O plus, which I'll write as H2O with an extra acidic hydrogen coming off. And we're simply going to steal the hydrogen there. And yes, this will get us back to exactly where we were before we ever deprotonated that second alpha hydrogen. And a lot of students say this is really stupid, and even though it is, and you already have the product, if you're drawing the mechanism, this actually happens, and it has to be done. So there you have it, our final product from this Claisen reaction. For intramolecular Claisen reactions, they are going to be very similar to intramolecular aldols, except the dicarbonyl in these is specifically a diester. So an enolate formed on a diester will react intramolecularly if a 5 or 6 membered ring can be formed. And what we're going to do, this process for getting to the product, is very similar to the process that we used for the intramolecular aldol. Now for this, I am not going to show the entire mechanism. If you want to know the mechanism for the Claisen, just go back in the video. It's the same idea. You need to have at least 2 acidic alpha hydrogens on the ester in order to carry this out. So the mechanism is exactly the same. What we're going to focus on is just how do we get to the product quickly. So of course the first thing we're going to do is we're going to locate all the alpha carbons on the diester that have at least 2 alpha hydrogens. In the example down below, it appears we only have 1 alpha carbon with 2 hydrogens. That's on this left side here. The right side only has 1, so that side's not going to work. So we're only looking at the left side here. And we're going to count the number of carbons from those alpha carbons that have at least 2 alpha hydrogens to the opposite carbonyl carbons. So we have 1, 2, 3, 4, 5, 6, and as long as the answer is 5 or 6, an intramolecular Claisen reaction can occur from that position. So now what we're going to do is we are going to draw a 5 or 6 membered ring, in this case a 6-membered ring, labeling the alpha carbon with the number 1 and the carbonyl carbon with the 5 or the 6. Again, this time it is going to be a 6. So here's our 6-membered ring. And it doesn't matter what we call the 2. What's important is that we just know that this 1 is going to be in this upper left-hand side. And I actually, for the intramolecular Claisens, I prefer to label the 2 going downwards. It doesn't matter because we can rotate bonds. So I'm going to go downwards here, and I'm going to put the 6 at the top. And you'll see why at the end. It just makes for a prettier looking final product rather than having the 6 be on the bottom. So now what we're going to do is we're going to attach the double bond O to the carbonyl carbon at that 6th position. So we know we have this right here. And then we're going to draw everything else at the appropriate numbered carbons. So what did we have at carbon number 1? Well, if you look over here at carbon number 1, what did we have? We had the rest of the ester. So we're going to draw in the rest of the ester now. At carbon number 5, we had a methyl group, so we're going to make sure to draw a methyl group at carbon number 5. And you may be thinking, oh, we also need to add that OET back on at carbon number 6. But remember, we don't need to do that because in this mechanism, which I will show the second step here, we were going to have this enolate. And this enolate was going to do a substitution at this position. And remember, when we do the substitution, we kick off the leaving group. So we don't actually need to have that on there. So there you have it. That is our product of the Claisen, the beta keto ester. Last up for the Claisen section of this video, let's talk about Claisen-like reactions, or Claisen-related reactions. So a Claisen reaction technically occurs only when 2 esters are involved. There are many reactions that are Claisen-like that don't involve 2 esters, but are still condensation reactions that still go through the substitution mechanism. So let's take a look at this reaction that I have drawn right here. Before we can answer this question, we should have to figure out whether the enolate is going to form on the aldehyde side on the left or on the ester side on the right. And to answer this, we should evaluate which alpha carbon is more acidic. So in other words, we have alpha hydrogens in these 2 locations, and we have to say, okay, is the aldehyde alpha carbon more acidic, or is the ester alpha carbon more acidic? Now, hopefully you know this at this point, but we shouldn't really ever try to evaluate acids directly. We should always evaluate the stability of their conjugate bases. So again, the stronger the acid, the more stable or weaker its conjugate base. So I've drawn the conjugate base of an aldehyde and the conjugate base of an ester down here. Again, you can see that all I did was remove the acidic alpha hydrogen. And now we're going to evaluate which one of these conjugate bases is more stable. So the most important thing we're looking at here is we're going to draw resonance structures. So you can see with the conjugate base of the aldehyde, I can draw a resonance structure that puts the lone pair and the negative charge on the oxygen. So in other words, we have a major contributor to the resonance hybrid because we always like to have negative charges on more electronegative atoms in resonance, and we have this minor contributor to the resonance hybrid. Of course, we can do the same thing with the conjugate base of the ester. and that is going to give us this resonance structure here. And again, this one is going to be major on the bottom, and the one on the top is going to be minor. However, we have another oxygen with lone pairs on the ester side. And what can we do with this? Well, we can actually donate electrons via resonance with this oxygen. So this is going to be conjugated with this double bond here, which means we can have another resonance structure, which puts the lone pair back on the carbon, which of course is unfavorable because we would rather not have the lone pair on the carbon because we want it to be on the more electronegative atom. So even though this is also a minor contributor to the resonance hybrid, all of the minor contributors still have some effect. So in other words, we have two minor contributors to the resonance hybrid with the conjugate base of the ester, and those two put the lone pair and the negative charge on the carbon. And this is actually going to make the conjugate base stronger and more reactive because we don't like to have lone pairs on carbons because they're not very electronegative, so they give up their electrons quickly. And since they give up their electrons quickly, they are going to be more reactive and therefore less stable. So the stronger the acid, the more stable its conjugate base. So in this case, the aldehyde conjugate base is going to be more stable than the conjugate base of the ester. Therefore, the alpha hydrogen of an aldehyde is going to be more acidic than the alpha hydrogen of an ester. Now, with that being said, we know that when we use OET negative, we are going to actually deprotonate the aldehyde's alpha carbon instead. So we're going to go through and follow our process where we number from the alpha carbon to the other carbonyl. And we know this is going to be a substitution because we have a good leaving group, and that's why this is a Claisen-like reaction. So when we draw our product, all we need to do again is we're going to start from that one position. We know we have a 6-membered ring, so 1, 2, 3, 4, 5, and 6. There's our 6-membered ring. We can number that now. And again, I like to number it going downwards for Claisen-like reactions as opposed to going to the right. So at the 6, we know that we still have our double bond O, and we kicked off that leaving group. And at the 1, we still have the aldehyde. And that would be our final product. Next up, we have the Michael reaction, and the Michael reaction occurs when an enolate reacts with the beta carbon of an alpha-beta unsaturated carbonyl rather than at the carbonyl carbon, which is what we've been attacking with enolates. Now, an alpha-beta unsaturated carbonyl is also known as, in this chapter, as the Michael acceptor. So let's take a look at a reaction here. We start out with a ketone, and we are going to react it under kinetic conditions to give us the kinetic enolate. And once we have the kinetic enolate, we're going to do a second step where we react that enolate with a Michael acceptor that is drawn in blue. And as mentioned, the enolate is going to selectively attack the beta carbon of an alpha-beta unsaturated carbonyl or Michael acceptor instead of the carbonyl carbon. So we're going to attack right here, and that's going to send the double bond down to put a lone pair at that alpha carbon position. And like is the case with all of these condensation reactions, the hardest part is actually drawing the product properly, not necessarily understanding what is happening from a mechanistic point of view. So we are going to draw the enolate, or what is left of the enolate still in red. We're going to draw our new bond to that beta carbon, and then we should be careful about what is going on at that beta carbon. Notice at the beta carbon, I'm still attached to 2 methyl groups, so let's draw in those 2 methyl groups. And we're also attached to the rest of that aldehyde, so let's draw in the rest of the aldehyde now, and now we have a single bond. So now we have this, and of course we did put a lone pair in that position. So the last step here is very simple. We're just going to protonate with water to get rid of the lone pair And right there we have our final product. Now, rather than simply accept the fact that enolates attack beta carbons of Michael acceptors, it's probably better to understand why it's even possible to attack them. Because in chemistry, we're always drawing arrows from negative charges to positive charges. So in order for this to happen, we must be saying that the beta carbon of a Michael acceptor has a positive charge and is therefore an electrophile. So why is that the case? Well, if we actually look at the Michael acceptor down here, we can draw a resonance structure because this is conjugated with the double bond O. So we can draw a resonance structure like this. And once we draw the resonance structure, you can see that we do have a charge separation that puts a positive charge on that beta carbon, which is why we're allowed to attack it with the enolate. The Robinson annulation is a multi-step reaction that combines a Michael reaction with an intramolecular aldol reaction. And what happens is it will always result in an alpha-beta unsaturated carbonyl, where both the carbonyl carbon and the alpha-beta double bond are found in the same 6-membered ring. Rather than show the entire mechanism, I'm going to show you the quick way to get to the product of a Robinson annulation. The first thing we need to do to recognize whether we're doing a Robinson annulation or not is to look at the reactants. You will always have a Michael acceptor, or an alpha-beta unsaturated carbonyl, and an aldehyde or a ketone with an alpha hydrogen. You also need some way to generate an enolate. In other words, you need a base. Now, the other thing, we have to have the Michael acceptor having 2 acidic alpha hydrogens as well in order for it to participate in the intramolecular aldol reaction that forms the ring, and then the subsequent E1CB mechanism. So if we look at the reaction we have in the bottom here, notice I have a Michael acceptor right here. And on the Michael acceptor, I also have this alpha carbon, and it has 3 alpha hydrogens. It needs at least 2. I have another carbonyl that has acidic alpha hydrogens. So we have a very acidic alpha hydrogen at this carbon position. It's not drawn, but it is there. And then we get this product over here. And just looking at this, you may be thinking, how do we get that? And that's a very valid question. And again, it is 2 things, a Michael reaction, then the intramolecular aldol, followed by the end of the aldol, which is the E1CB mechanism that we talked about earlier in the video. Now, the most important thing here is lining everything up properly. So in step 2, it says line up the Michael acceptor so the double bond O and the carbon-carbon double bond are facing away from each other. So what does that look like? That should look like this. The double bond O and the carbon-carbon double bond facing away from each other. And then we're going to place the most acidic alpha carbon, the one that makes the enolate. We're going to place that next to that beta carbon. So here you can see that the most acidic alpha carbon is the one that is the shared alpha carbon between those 2 carbonyls. So right here, that is placed next to this position, the beta carbon on the Michael acceptor. After this, we're going to draw 3 bonds. One bond is made between the beta carbon of the Michael acceptor and the most acidic alpha carbon on the other carbonyl. That's why we lined those up. So we're going to draw a bond right here. And then a carbon-carbon double bond, so we're drawing the other 2 bonds, the double bond, is made between the alpha carbon on the Michael acceptor and the carbonyl carbon on the other compound. So in other words, it's kind of going to overlap over this blue double bond O. So we're going to draw this double bond. It's going to overlap over this. So just like that. And then we're going to remove 3 bonds. The original carbon-carbon double bond should now be a single bond, and the double bond O, both of them on the carbonyl that isn't the Michael acceptor, is also going to be removed. So when we draw that, we're going to erase those 3 bonds. So let's draw it like this. And you can see here that we have gotten rid of this bond right there. And we've also gotten rid of this double bond O. So again, this is step 3 right here. And then this right here is step 4. Let me erase those 3 bonds. It is possible that you'll be asked a test question that requires you to know the mechanism, the entire mechanism, of a Robinson annulation. So once you recognize that a Robinson annulation is possible using the steps from the previous part of the video, we're going to line up the molecules exactly like we did to do it the quick way to get to the product. Once you have it lined up, we know that we're going to do a Michael reaction followed by an intramolecular aldol. So all we need to do is make sure that we know how to do those. So first we're going to look for the acidic alpha hydrogen in this position on this carbonyl right here, and we're going to use the base to deprotonate it and create an enolate. After the enolate is created, we're going to carry out the Michael reaction. So the enolate is going to attack the beta carbon on the Michael acceptor, and we're going to move the double bond and make it into a single bond, and we're going to put a lone pair on that alpha carbon. Next up, we are going to use our alcohol that we generated, and we are going to protonate that lone pair. That finishes the Michael reaction part of the Robinson annulation. Next, the base is going to come back in, and now it is going to remove the alpha hydrogen from the other side of what was the Michael acceptor. This will create the enolate that we can use in the intramolecular aldol reaction. Now, this enolate is going to attack via the addition mechanism the electrophilic carbonyl carbon. The double bond is going to break and go up to the oxygen, giving us an O negative. Notice since I don't have an aldehyde anymore, I'm going to drop off that hydrogen because we typically don't draw hydrogens on carbons in organic chemistry. Next, of course, that alcohol that we just regenerated is going to be used to protonate that oxygen. Now, because this was an intramolecular aldol reaction, we should know that we should be doing the E1CB mechanism to finish off the reaction. So that means we're going to have this OET, this base that we keep forming and breaking and then reforming. It is going to come in, and it is going to remove the other alpha hydrogen. That will create the enolate that is needed to carry out the E1CB mechanism. In our final step here, that enolate will go form a double bond and kick off the OH leaving group. This, of course, is our final product, which we said was a carbonyl where both the carbonyl and the double bond were on the same 6-membered ring, and it's an alpha-beta unsaturated double bond on that 6-membered ring. Now that we've gone through all of the condensation reactions, let's look at retrosynthetic analysis of each one. Let's start with the aldol reaction. All aldol reactions are addition reactions. That means the initial reactants are aldehydes or ketones without a leaving group. And because we mentioned you can only get 2 general products from the aldol reactions, whether it's a beta-hydroxycarbonyl or an alpha-beta unsaturated carbonyl, that should tell us exactly what we need to do to get to the starting materials. So I have 2 things drawn down here. One is a beta-hydroxycarbonyl, and the second one is an alpha-beta unsaturated carbonyl. And as soon as we recognize that that is what these are, all we need to do is say, where was the new bond created? And it is always created in an aldol reaction between the alpha and the beta carbons. So what we're going to do is we're going to cleave that bond between the alpha and beta, and same with on the second one. We're going to cleave that bond. Now, the side of the molecule that has the carbonyl, we're just going to draw it exactly as it is. So for both of these, I'm going to draw them just as the ketone, just like that. The other side of the molecule will either have an OH, if it was a beta-hydroxycarbonyl, or it won't have any oxygens. If it has an OH, all we're going to do is replace the OH with the double bond O. So in other words, we can get this as our other starting material. In the bottom one, we're going to put the double bond O exactly where the carbon-carbon double bond was. And that's all you need to do for retrosynthetic analysis of aldol products. Now let's look at retrosynthetic analysis for Claisen and Claisen-like reactions. All Claisen-like reactions, if you remember, are substitution reactions. That means that at least one of the initial reactants had to have had a leaving group. And usually that leaving group, we can just say it was something like OET, although it could be something else. Your product in Claisen-like reactions will always be either a beta-keto ester or a beta-diketone, or even a 1,3 diester. For example, if one of your reactants is an ester and the other has two leaving groups, we'd get a 1,3 diester. In other words, the product will have two carbonyls with a shared alpha carbon. So the most important thing is recognizing that we did a Claisen reaction. So if we look at what is drawn on the bottom here, we are looking for two carbonyls with a shared alpha carbon. Here it is. Here's the shared alpha carbon in this position right here that I circled in blue. If the product is a beta-diketone, you can cleave the bond on either side of the shared alpha carbon because that means you had two potential sets of starting materials. If the product was a beta-keto ester, cleave the side of the alpha carbon that is closest to the ketone. So here, because this is a beta-diketone, it's two ketones, we can cleave either one, which means we're going to get two potential sets of starting materials. So let's cleave this one on the right first. We're going to attach a leaving group to the carbonyl carbon immediately next to where we cleaved that bond. Then we're simply going to draw the other side of the molecule as is. Now we could have also cleaved the other bond. So if we had cleaved this side instead, we would have gotten two other starting materials. Notice that in this case, the two starting materials were actually part of the same molecule, meaning that this would have been an intramolecular reaction. Last up, we're going to look at retrosynthetic analysis of the Robinson annulation. Remember that the Robinson annulation will always result in an alpha-beta unsaturated carbonyl, where both the carbonyl carbon and the alpha-beta double bond are found in the same six-membered ring. So if we look at what I have drawn below in red, we can recognize that product is likely the result of a Robinson annulation. Although if you thought about it, you could also make the claim that it could have been an aldol reaction as well. But in this case, we're going to treat it as if it were a Robinson annulation. First thing we're going to do is we're going to cleave the double bond on the product. So here's the double bond, we're going to cleave that. On the opposite side of where we cleave the double bond, we're going to label the alpha and beta carbons. Next, we're going to cleave the bond after the beta carbon. This is going to break our product into two components. On the component that we labeled with the alpha and beta carbons, we're going to make an alpha-beta double bond. That part of the molecule is now complete. This was the Michael acceptor in the Robinson annulation. On the component that's left over, we're going to draw a double bond O where that original double bond that we cleaved was. This molecule initially formed the enolate that reacted at the beta carbon of the Michael acceptor. Those are the starting materials for that Robinson annulation product.